Sure.
Okay.
Oh yeah, the mic. Yeah. I think this thing is broken. Did you notice that?
Oh.
I can always just attach it to my button or something, but do you know what might be wrong with it? Okay.
No, okay.
Should I just do this?
Yeah.
Okay.
Yeah, I think you have to project a little louder since it's kind of low.
Okay. Maybe if I just put it in the higher button?
Yeah. Sorry, like previous professor broke it.
Uh-huh. Got a little too enthusiastic. All right, I'm going to get started. So the topic of this class will be how to do better, how to learn faster using policy gradient methods, using variance reduction and other alternative techniques for estimating the policy gradient. So first I want to talk about an idea called reward shaping, which actually underlies some of the ideas we'll be going into later on policy gradients, though this idea was actually proposed in a different context, not in the policy gradient context, but for a different, more general RL context. So actually I'm going to read, I just put this slide in so that when we put the slides online, people will have the sketch, but I'm going to draw all this stuff on the board now. So let's just draw a very simple MDP, and I'm going to introduce the idea of reward shaping using this simple MDP. So in particular, we'll define this chain MDP. So the chain MDP has, the states are a set of integers. Let's say we start off at negative m, and then we go all the way to n. So they're m plus n plus 1 states, and from each, the endpoints are going to be sync states or terminal states. So when you reach the endpoint negative m or n, you get stuck there. But at any other state, you can choose to go left or right. So the action space is there are two actions. One is to go left and one is to go right. The dynamics are totally deterministic. And the states are just the points on this number line, the integers. And the reward function we'll define to be 1 if, well, let's just write the argument. So reward of SAS prime, let's use lowercase r. So reward of SAS prime equals 1 if SAS prime is n minus 1 right n. So that means you get a reward of 1 if you do this last transition and get stuck on the right side. but you get a reward of 0 everywhere else. So the optimal policy here is just to always go to the right. It's pretty simple. So this is our, we can turn this, I mean, this is an MDP. It's a random walk on the number line if you have a stochastic policy. So to start out, let's say you have a stochastic policy that goes to the left half the time and to the right half the time. So it's the uniform random policy. And let's say you start off at 0. So your initial state is 0. So this is one of those interview questions. Does anyone know what the probability is? What's the value function here? So what's the probability that you'll get stuck on the right before you get stuck on the left? 1/2? Well, let's say m is not equal to n. So let's say n is much bigger than m. Then it's much more likely that you'll get stuck on the left before you get stuck on the right. Maybe. Anyone have any ideas on how to solve this?
N over, so like the proportion, so n over the sum.
And why is that? You just have an intuition? So there's a neat trick here, which is that you can say, OK, let's say we're at a given point. Let's say we're at k. This is state k. So there's half a probability of 1/2 that will go to the right to k plus 1, and probability of 1/2 that will go to the left to k minus 1. So that means that probability at state k is going to be 1/2 times the probability at k minus 1 plus 1/2 at probability k plus 1. So the value at any point is the average of the two neighbors. And that implies that the function is linear. Because if you can turn it into a recursion where you just end up with pk plus 1 equals 2pk minus pk minus 1. So you end up getting that it has to be a linear function. So that means that if we have a undiscounted, actually if we also have a discounted problem, we end up with a linear value function for this problem, or linear in the index. And it's going to be 0 at this. It's going to be 0 at this state on the left and 1 at the state on the right. So the value function has to be. You can work it out that it's going to be n over n plus m. So you're right. OK, so that's just as a little warm up on the problem. But now let's talk about rewards and shaping. So let's talk about this as an MDP. I'm going to erase the board. So let's say we put time on the x-axis, and first on the y-axis, let's put position. Let's call it x, or let's not call it x because that's a little confusing. Let's call it index. So we start off at 0, and then we might go to the right a little bit, and then to the left a little bit, to the right, left, right, and then let's say we end up all the way at the terminal state on the right. So this is n. So now what does the reward function look like? So let's draw a new plot with the same x-axis, and the reward is going to be 0 for all time steps, and then it's going to be 1 at the very end. So the reward is just like, and then a little spike at the end. So now if you think about trying to learn in this MDP, you're not getting any reward for all of this time, and then suddenly you get a reward at the very end. So it seems like it would be really hard to learn, because what you really want to do is say, oh, these actions when I was going to the right, those were good, and the ones where I went to the left, those are bad. So you want to assign credit to the different actions along the sequence. But since But we're not doing that. We get, I mean, it's not obvious exactly how to do that credit assignment. That's what makes RL hard. So, so if we do a policy gradient method, then all we're looking at is the returns, the sum of future rewards, and we're just going to increase the probability of all the actions that preceded this reward. If we got a reward, then our policy gradient estimator looks like grad log probability times returns. So we're going to try to increase the probability of all these actions. But actually, some of them were good when you were going to the right, and some of them were bad when you were going to the left. So not all of them are good. And what we're really doing is we're confounding the effect of all these actions. That's the problem. So that's sort of the state of things in RL. That's the big credit assignment problem. So what would we like to do to make this situation better? Well, it would be nice if we could have a reward function that was more informative that we could learn from, instead of using the original reward. Let's say instead of using, let's say we use a reward function that measures how far to the let's say we change the reward function and say, if I move a little bit to the right, I should assign a little extra reward for that. So let's define our new reward function, r tilde of SA S prime, to be r of SA S prime plus, let's just say it's going to measure, actually I'll leave out the discount for now, phi of S prime minus phi of S, where phi of S is something that's linearly increasing with the state index. So that means if you go to the right, this thing is going to be positive. This difference will be positive, and if you go to the left, then it'll be negative. So let's just say we want to give the agent a hint, or we want to give the policy gradient method a hint that it should go to the right. We could add a little term like this, which is giving you a reward or penalty for the difference in the state. And if we do that, then we'll actually end up with the reward function that does what we want. So it'll be positive when you're going to the right, then it'll be negative when you're going to the left. And then if you learn from that, it seems like you have a much more informative reward signal. So that's sort of what we want to do, and now we need to try to justify that. Yeah?
If you were to solve like an MDP for some reward function, and then you replace the reward with the value function, you get out the same optimal policy.
Oh yeah, so that's exactly where we're going to go very soon. That's what we're going to talk about very soon. So I was hinting about thinking about the value function before. So it seems like what we want to do is use the value function somehow to define a new reward function. So then that brings us to the actual more formal statement of this idea. So we're going to define reward shaping as a transformation of the reward function where we use a potential called phi. Phi is going to be called a potential function. And the question is, if we transform the reward this way, does this new MDP have any relationship to the old MDP? And it turns out it has exactly the same optimal policies as the original MDP. That should be lowercase r. When we do this reward shaping transformation, and we have a discount gamma, so the optimal policy according to the gamma discounted return is the same as the optimal policy before reward shaping. So that's actually a kind of non-obvious fact. I mean, it's a very simple fact, but for some reason, as far as I know, it didn't appear in the literature before this paper, this 1999 paper. Mm-hmm.
So there's no condition on the potential, right?
Right. The potential can be anything at all. Yeah. It sounds a little weird, but soon you'll see why it's true, and it'll be kind of obvious. So the proof in the paper is based on the idea that first you say that, let's say we have an optimal Q function, Q star, which satisfies the Bellman equation with the max. So the Bellman, it's a fixed point under this max Bellman backup. then this transformed Q function also satisfies it. And you can show that if you do the reward shaping transformation, then the Q function gets transformed by subtracting out this potential. So the proof says that if you do the reward shaping transformation, then and you execute the same policy that you were executing before, the Q function gets shifted by this potential phi, and then the new Q function satisfies still satisfies the Bellman equation. So if you want to find the proof, you can look at that paper. But here's an alternative proof that I find a little bit more intuitive. And the idea is that you end up with this nice telescoping sum. When you add up this discounted sum of shaped rewards, you end up with a nice discounted sum. So let's just consider what happens if you take the expected sum of discounted rewards. Okay, ignore this line. So we're starting off with this expected sum of discounted rewards. And okay, so now we write it in terms of the original reward and the shaping potential. And then we notice that some terms cancel out. So gamma phi of S1 appears in both with a positive sign and a negative sign. And same with gamma phi of S2. It appears with a positive sign and a negative sign, and gamma squared in front. So everything cancels out except for the reward terms and then the last potential. So what this showed you is that when we take the expected sum of these shaped rewards, we get the original expected sum of rewards minus the potential function at the first state. And remember, ignore this first line, which shouldn't be there. Okay, so that tells us how the value function and the Q function are going to transform when you do this reward shaping transformation. So the value function, if we have the value function of the policy, that's defined by taking this expected sum of rewards conditioned on the first state. So that's going to get shifted by phi. And same thing with the Q function. Here we just have, with the Q function, we just have this expectation, but it's conditioned on this first state and the first action. So the Q function also gets shifted by phi. And that means that the advantage function is totally invariant under this transformation. Because the advantage function is just the Q, this should say Q of SA. The advantage is just the Q function minus the value function. So under this reward shaping transformation, if we have a fixed policy, the advantage function is unchanged. And if you remember the, well, first of all, if the advantage function of a given policy is 0, it must be the optimal policy. Or if the advantage function is 0 at the states, at all the actions taken by that policy, then it must be optimal. So that's something that's something that we went through when we talked about policy iteration. I mean, yeah. So if the policy satisfies a advantage function of s and pi of s equals 0, so that means it's the optimal policy. Yeah.
Can you say what are the conditions on the potential function again?
No conditions at all. It's any old function. So yeah, if you add anything to the, so basically this is just showing that if you if you do this shaping with any old potential function, yeah, it'll change the individual rewards, but when you add them all up, all of these, it adds a state-dependent term to the returns, but it doesn't add an action-dependent term. So if we consider two different actions, so actually another way to look at it that makes it more obvious is, let's say we start at a given state, and then we have two possible actions we can take, action 1 and action 2. And let's say our MDP is such that you always end up in the same place at the very end of, at the end of the episode. And that's kind of true because if we have, if you end up in a terminal state, we can say that there's only one terminal state, right? So it's safe to say that we always end up in the same state. So let's say both of these actions go do something different, but then end up in the same state. So if we look at all of the shaping terms that we got along these two paths, they all everything cancels out except for the value function at the beginning. So if we consider, I mean, at each transition we get this little shaping reward phi of st plus 1, or gamma phi of st plus 1 minus phi of st. This is what we're adding. So when we add all these terms up, everything cancels out except phi of s0. So we're adding the same. That means we're adding the same thing to both of these paths. So so that means we're not changing the difference in the returns for two different actions, or we're not changing the difference in paths that start and end in the same place. That's kind of the key thing.
So, let's say I give you the example when you define the phi function to increase as you go to the left, to the point where like now even the reward on the left side is some number greater than 1.
Uh-huh.
And I'll make phi decrease going to the right. And I'll make the reward on the right side a number that's less than 0.
Right.
Fundamentally change the solution of the
So you have to make sure everything is bounded for this result to hold. If you don't, then you can, yeah, so you're coming up with a good counterexample. If you were trying to construct a counterexample, that's sort of the right idea. What if you try to make it so the reward is, or the potential is getting bigger and bigger? But if you make sure everything's bounded, then all this argument works out. Yeah.
The question is in the very beginning of the intuitive example, which is you give a reward of 1 when you go right, and then minus 1 if you go left. That kind of depends on action instead of only depending on the state, right?
Right. Okay, so the question is, in the example with the random walk, wait, I don't understand exactly the question, actually.
So the reward shaping is that you have a shift which is based on the state, right?
Yeah.
In the very beginning, so the reward shift, the change you made in the reward is that every time you go to the right direction, you get a positive reward.
Yeah.
And when you're going to the left side, you get a negative reward, right? So
Yeah.
there are two ways to enter a state. And so different ways of entering different state, you get a different reward, right?
Right.
But that's kind of depends on action.
Yeah, so to recap the question, in the random walk case, if you, the change we made to the reward function sort of depends.
Sorry, I got it. So it's
You got it.
difference,
Okay, yeah, just to recap it for the video, so the question is, like in the reward shaping we did at the beginning on the random walk problem, we were incentivizing you for going to the right. So that's like an incentive based on your action. So that seems like a different kind of shaping, but in fact, it's defined in the same way by looking at a difference in potentials. So, okay, so this is the reward shaping idea. And there are a couple of nice corollaries. So one thing that's pointed out in the paper is that if you use the optimal value function, the optimal state value function as your shaping potential, then value iteration solves the problem in one iteration. It comes up with the optimal. Well, it's already, value iteration is done. It already, well, if you start with, let's see. So value iteration is going to, you initialize the value function somehow, and then you do a backup. So you set the value function to be reward plus gamma times next value. So you take expectation of reward plus gamma times next value. That's value of s. So if you take, if we replace reward by the shaped reward, then we have reward plus gamma times v star of s1 minus v star of s0. And then we're adding, let's say we initialize the value function at 0, and then we do one step of value iteration. Then that means we're going to set v of s to equal the expectation of this quantity. Let's see. Well, I guess it'll give you the optimal policy after one iteration. So if we take the argmax, sorry, I should have said that this is max over actions. So if we take the argmax over actions, then let me erase the board so I can write this out a little better. So we have, let's initialize v of s to be 0 everywhere. And then we want to do value iteration. So we're setting v of s to max over actions of expectation over s prime of reward of s a s prime plus gamma times next value. And here we're saying that we're initializing the value function at 0, so this term is going to vanish. And let's say we use the transformed reward function. Then we're going to have max over actions of reward s a s prime plus gamma v star of s prime minus v star of s. So maybe I said the wrong thing. So, problem is solved. Yeah, that's right. In that you have the optimal policy after one step, you don't have the correct value function after one step, obviously, because that requires, you're going one step look ahead every iteration. So that's still going to take a while to converge. But you have if we take the argmax, which is the policy, the greedy policy we're defining, then that's going to be the optimal policy, because we said that the original reward and the transformed reward have the same optimal policy. And I mean, by definition of v star, we have that argmax over actions of expectation of rewards s a s prime plus gamma next times next value. This is going to be the optimal policy, pi star of s. So clearly we're going to get the optimal policy when we do one step of when we look at the greedy policy on the transformed MDP, even if our value function is 0. So that's kind of cool. It also, as we pointed out before, it leaves the policy gradient invariant, because you have, let's say we just write out the discounted sum of returns times grad log probability. As we said before, this just, all the extra shaping terms cancel out except the first one. But remember, with policy gradients, when you add a baseline, a state-dependent term to the returns, it doesn't, or you add a term to the returns that is a function of the state that your action is conditioned on. So if we add, if we take this expectation, it's independent of phi. That's just something we talked about when we introduced policy gradient methods, and this is why we're allowed to use a baseline, why the baseline doesn't introduce bias. So that way you can see that this policy gradient estimator with the shaped reward is the same as, well, it's actually, the estimator isn't exactly the same because this one has a baseline in it, but the policy gradient is the same because the expectation is the same of this term. Yeah, and another way you can see that is by looking at the advantage function. So actually, this is this is like reminiscent of a calculation we showed in the last class where we were talking about this identity involving the policy performance and the advantage function. So if we look at the expectation of this change in, this should say that should say, oh no, this is right. Okay. So if we look at the expectation of this shaped reward, where we use the state value function v pi as the shaping potential, that's just the advantage function. So, okay, so now let's do something a little different from what we did in the last slide. And let's say we're going to write down our policy gradient estimator, but we're going to we're just going to look at the first reward. So we should, if we want to write down a proper unbiased policy gradient estimator in general, we have to take the sum of discounted rewards starting at time t. But let's just write down the first reward and ignore all the future ones. Okay, we write it out, we expand it out like this, and then we notice that we can replace it by this difference by the advantage function. So, so lo and behold, we got the correct unbiased policy gradient. Even though we ignored all of these, those discounted, we ignored all the terms we were supposed to include in our discounted sum of rewards. So it's like we pretended that our discount was 0 after doing the shaping, and we got the correct policy gradient anyway. So that's kind of, that's a little bit weird, isn't it? And we'll show in a few slides a different way of getting at this that is more justified, or shows a more general form of this, this kind of identity. But just to sort of preview what we're going to do later, let's say this only holds. So we only get this unbiased policy gradient estimate if we shape using the state value function, the correct state value function. But in practice, we have to estimate the state value function. So we're gonna have a wrong state value function, and we're going to get a biased policy gradient estimate. I mean, it's clear that it's going to be biased in general if we ignore all these reward terms, because let's just say the value function was 0. Then clearly we're just looking at grad log probability times first reward. That's not going to give you the right policy gradient. So clearly this is going to be biased in general. It's just unbiased if you happen to have the exact state value function. But so we could imagine doing a compromise between this policy gradient estimator and the original one, the original unbiased one, where we take some kind of more aggressive discount. So instead of using 0 as the discount, we use gamma lambda for some lambda less than 1. And this could presumably give us something that's that has less variance, because we're adding up less terms here or this term here has lower magnitude in general. But we're going to have some bias, but not as much bias. This was kind of very sketchy, so we're going to go through this more in a more formal way shortly. So just as a summary of this discussion on reward shaping, and then I'll let you ask some questions. So reward shaping transformation leaves the policy gradient and the optimal policy invariant. All it does is shifts the state value function, the value function and Q function by a constant. And shaping by using shaping intuitively, what it does is it makes the consequences of your actions more immediate. So going back to the random walk example, if we shape using our value function, which was this linear function, then it gives you a reward for going to the right, the correct direction, and it gives you a penalty for going to the left, which is the wrong direction. So the shaping is giving you more like immediate feedback on whether you're doing the right thing or the wrong thing. It's bringing your rewards closer. And oddly enough, if you do shaping with the state value function, and that's the important caveat, and ignoring all but the first term, gives you the correct policy gradient. Okay, so that's any questions before I move on? No? So, yeah.
So it seems like this type of reward shaping is very general. It works for like any arbitrary phi. But are there other schemes where like with more conditions on phi that there's like different ways that you can do shaping and still get out similar properties?
Yeah, that's a good question. So you can find, so the question was, is this the most general kind of shaping, or can you do, is there another kind of shaping you can do that'll also give you, well, that'll have similar properties, or some of the good properties? So the paper talks a little bit about this, and they show that I don't want to make an incorrect statement, but this is the if you make I think if you have something that's time independent and it's like okay, there are definitely ways you can transform the reward function that'll give you the same optimal policy. So there are going to be lots of different reward functions that have the same optimal policy. There's some general condition that for which this is the only kind of shaping that's valid. I don't remember exactly what the condition is, but you can find it in the paper. Yeah. Okay, so also here are just a couple. So reward shaping is actually very important in practice if you're trying to get an optimal control system to work. So these are two. These papers are not using reinforcement learning. They're using trajectory optimization. But I like these are two of the most impressive demonstrations of like trajectory optimization on continuous control problems, like simulated robotics problems. And both of them, if you look at any of these papers that do something impressive with, say, humanoid locomotion or humanoid, any kind of simulated robot behavior, people usually spend a lot of time crafting the reward function so that it'll give you hints about what you should be doing. So just from this paper where they show how to get these little critters to get up off the ground and climb over things and all sorts of things just from trajectory optimization, they have to construct this reward function or cost function that's like, they have some term that's, well, I'm not going to go into all the details, but they have a bunch of different terms that give you hints about how to do it. And they go to great lengths to make it nice and smooth. And this paper is showing how you can just define reward functions and define the dynamics for simulated humanoid robot that will allow you to just use trajectory optimization and automatically get behaviors like getting up off the ground and learning how to walk and run. And they also talk about how add together lots of different terms to make sure that the reward function is giving you a hint about all the different things you should be doing. So that's a big part of this of all of these getting things to work in reinforcement learning that people don't talk about a lot because it's sort of I guess it's application oriented and it's also sort of it's independent of the algorithms. And some people might consider it cheating a little bit to make to design a reward function so that the problem is easier. But on the other hand, it's what you need to do, and it's like one of the most effective things you can do to make real things work with either trajectory optimization or reinforcement learning. If you look at the some reinforcement learning robotics problems like this that are solved with reinforcement learning, you'll see that people do the same kind of thing where they define some reward function with a bunch of different terms that were weighted through some kind of careful tuning process. Okay, any questions? Mm-hmm.
Can it go the other way too, where sometimes is there ever a case where it's better to use this a more sparse reward function?
So the question is there any case when it's better to use a more sparse reward function? Not that I know of, but maybe there would be, yeah. Well, it might be better for something. It's going to be, if you're just trying to solve the problem with reinforcement learning, it's probably going to be harder. Yeah.
Right, and for reinforcement.
Yeah. Okay, so now we're going to cover some of the same ideas, but just come at it from a slightly different angle, which is how to do variance reduction and how to make bias variance trade-offs when in policy gradient methods. So to start off, we've got this formula for the policy gradient, which, I mean, there's a whole bunch of different formulas you can write down where you've got grad log probability times something here, which is either the returns or the advantage or something in between. But in this formula tends to have a lower variance than anything that involves the Monte Carlo estimate of the advantage function. So what people would usually do in practice is take the sum of rewards minus a baseline, because that's what you can measure. But this is going to have lower variance because we're taking the expectation over all of the possible returns. So okay, this advantage is not known, but we're going to use an advantage estimator. So in the undiscounted setting, what you do is you take the sum of future rewards minus the baseline, and that's going to give you an unbiased policy gradient estimator. This is in the undiscounted case. And if you take the baseline approximately equal to the state value function, that's going to reduce the variance because it's going to just reduce the magnitude of this term right here. And you sort of want to, you're taking a Monte Carlo estimator of something, so we want to, if we have a choice between a bunch of different estimators with the same mean, we want the one with the smallest magnitude, so then it'll have the lowest variance. Okay, so now let's just look a little bit at what the problem is, and this is sort of related to our random walk discussion before. So what we're doing is we're confounding the effect of multiple actions, as we said before. So the advantage at time t, which is what we're using to update decide if action a sub t was good or bad, actually depends on lots of future rewards, and it mixes together. This this sum of rewards depends on all the future actions. So we're confounding together lots of effects, and this is a very rough statement, but roughly the signal and noise ratio of this advantage estimator scales as 1 over t, because we have t different, where t is the time horizon. So t is the number of actions that happen in the future. So the reason for that is we have this sum that depends on t different things. So we can say, let's say that they make t independent contributions to its value, and but only one of them. We're only interested in one of them because we're trying to decide if action a sub t was good. So the real thing we're trying to estimate, which is the advantage function of this action, only depends on this one, the first one. It doesn't depend on all these later ones. So that's why. So the signal to noise ratio is like we have one bit of signal and t little pieces of noise. So that's not so good. Another rough way of thinking about this is that when we do policy gradients, we're kind of doing finite differences in action space or in trajectory space, because we have we can collect a trajectory with t different actions, and then we collect a different trajectory with a different sequence of t actions, and then we're going to increase the probability of the one that has better returns. So it's like we have these two high-dimensional vectors of the action sequences, and we're increasing the probability of the one that's better overall. So it's kind of like if we have a big parameter vector and we make two little perturbations to it, and we move in the direction of the one that gives us the better function value. So it's kind of like doing finite differences in a space that has like time horizon times action dimension components. Okay, so then let's think about discounts. I thought I fixed the spelling. The discount factor downweights the effect of rewards that are far in the future, so it ignores these long-term dependencies. You're assuming by using a discount you're not assuming that the rewards in the future are going to be small. You're just assuming that they're not affected by the current action. So you're assuming that if I take an action at time t, it's not going to affect the reward at time t plus 1,000. That whatever effect it had is going to be washed out by everything that happens subsequently. And in some cases that's true, and in some cases it's false. So let's say lose my credit card one day, and then I don't know that I lost it. And then I go about my day happily, but then some fraudster picks up my credit card and deducts my whole bank account. And then 2 days later, I notice that I don't have any money in my bank account. So and then I am really sad, so my reward function is negative. So that was a lot of time steps in between. And so the action I took where I just left my credit card on the ground, that had a really delayed effect on my reward. So it's not always true when you make an assumption like using discounts. And it's actually pretty hard to do this kind of credit assignment. Okay, so the advantage, so we want to, as we said before when we introduced the idea of baselines, we want to make this advantage estimator have expectation 0, so we're going to fit the baseline to be as close as possible to the discounted state value function. The discount, using a discount is similar to using a a finite horizon of 1 over 1 minus gamma time steps, because if we just look at all the coefficients, 1, gamma, gamma squared, gamma cubed, and so on, and add those all up, it's 1 over 1 minus gamma. So it's like we're adding together 1 over 1 minus gamma, different rewards. This is a biased estimator of the advantage function. Well, okay, when we're this is kind of review from when we were introducing policy gradients. I just want to say this is, in the perspective we're taking here is that what you actually care about is the sum of the undiscounted sum of rewards. But we're going to introduce discounts just to get better variance reduction, just to get lower variance. So if you think about it that way, then this A hat is a biased estimator of the advantage function. So what we're going to do here, then what we can try to do is come up with even better biased estimators of the advantage function. So instead of using discounts, we can actually try to use value functions in the future instead of just ignoring rewards in the future. Let's say, instead of using this discounted sum of lots of rewards, what we can do is try to cap it off early and use the value function to estimate how many rewards you would have gotten in the future instead of looking at what happened empirically. I mean, because if you look at this big sequence of rewards, these future rewards depended on some intervening actions that happened. Maybe if we have a really good value function, we can just average out the effect of all possible future action sequences. So that's what we're doing here. So here we just look at the value function at the next time step. Now we look at the value function 2 time steps later, and so on. And if we do infinity time steps later, then we're back to where we started. So this is like a sequence of different estimators of the return that depends more or less on the value function. And another way of thinking about this all is that the baseline removes the effect of past actions because by the Markov assumption in an MDP, the current state, S, captures the whole effect of everything in the past. So nothing in the past matters except what's in S. And, or the future is conditionally independent of the past given S. So what the baseline does is it subtracts out the effect of S, and that means it's subtracting out the effect of the past. But now what we want to do is subtract out the effect of the future. If we want to, does this make sense? So here we're writing down a bunch of different estimators of the returns. And those were just estimators of the returns, but now we can write down estimators of the advantage function. So we subtract out the baseline. So these are different, these are biased estimators of the advantage function because of this discount factor. Though it's unbiased estimators of the, if we're looking at a gamma discounted return. So what we have is, we have that the first one is low variance but high bias, and the one with infinity time horizon has high variance but low bias. Can anyone tell me an argument why this one has low variance but high bias? Like, why should it have low variance? This is going to be a hand-wavy argument because there's not a particularly good formal argument.
Is it because it doesn't depend on future actions?
Yeah, so the suggestion was it doesn't depend on the future actions. Yeah, that's. Anyone have any other explanations?
Is the estimation based on like current functions, so it wouldn't vary too much?
Let's see. So the suggestion was it's not going to vary too much because it's based on the present instead of the far future. Is that what you're saying? Yeah. Yeah. So this is basically what's going on. I mean, this isn't always true because let's say the value function is like really, really large, way too large. Then you can make this arbitrarily bad and arbitrarily high variance. But let's say v is approximately equal to the state value function. Then this is on the same. This is basically. It only depends on the first action. So there's only. Let's assume that each action in the future introduces a fixed amount of variance. Then we only have variance from the first action. That's what's kind of hand-wavy about it. So the variance of a sum is not equal to the sum of the variance. So we can't say that this always has lower variance, but it usually is going to have lower variance. Yeah.
Well, why would it have low variance if the value function is bad? I guess like wouldn't it just shift everything? Yeah, like and then the bias would shift, but the variance would still be possible.
So the question is, why does this have low variance when the value function is bad?
Yeah.
That's your question?
Yeah.
Well, it can have arbitrarily high value variance if we make the value function bad. So we can just make the value function really large and make this have arbitrarily high variance. But if the value function is a decent approximation of the state value function, then it'll be lower variance.
Okay.
And actually another way, here's a good explanation of it. I wonder if I have this calculation on the next slide. Let's see. No, I don't. So let me do it on the board. And this will show you one explanation of why it has lower variance. Okay, here's my marker. So let's say we define delta sub t equal to reward t plus gamma times next value minus current value. So if we just take, now let's look at our first advantage estimator, advantage 1. Is that what I'm calling it there? Yeah. So advantage 1 hat sub t is just delta sub t, right? Advantage 2 sub t, I'll claim, is just delta t plus gamma times delta t plus 1. And that's because you get a telescoping sum, because you have reward t plus gamma times reward value t plus 1 minus value t, and then we add, that's delta t, and then we add gamma times delta t plus 1. And we get the v of s sub t plus 1 cancels out. So we're left with r of st plus gamma r, or rt plus gamma r t plus 1 plus gamma squared v of s sub t plus 2. So you can see that what we get is that the kth advantage estimator is just the sum of the first k deltas. So these delta terms here are like shaped rewards that use the value function as the shaping potential. So it's like these are finite horizon estimators of the return. That's the way you can think of these. These are finite horizon estimators that just use the shaped rewards and ignore all the ones in the after a certain cutoff. Does this make sense to people?
And what you have here is, at that point, v is just like, it's fixed, right? So it doesn't contribute to the variance. Or is it also changing?
Right, v is fixed here, yeah. Oh, so what I was trying to get at before is I was saying what's a good hand-wavy argument that we can come up with for why the A1 has lower variance than A infinity? Well, one argument is that if we pretend that the variance of the sum is equal to the sum of the variances, which isn't actually true in general, but we can pretend, then the variance of this is clearly going to be lower than the variance of this, and so on. But the claim is that they're going to have the same mean if if v is equal to the state value function, then they actually have the same mean. So that's the cool thing, and that's because the expectation of delta t plus 1 is conditioned on the first action is 0. Yeah.
So even though like, you can't necessarily break up the variance like that, but
Yeah.
if the variance of like let's say A, that should still be less than the variance of A.
Okay, so you're saying that. So the question is, well, we can't say the variance is the sum of is the sum of the variances, but can we say something like this? Not necessarily.
Oh, no, the other way. No.
Oh.
Like that's the variance of A.
You're saying that this is less than or equal to variance of A.
Exactly.
I don't think this is true either.
No, sorry, the other way.
Oh, greater than or equal to. Yeah, I don't think this is true either, unfortunately. I mean, well, I guess if they're independent, it's definitely true. So if A and B are independent, then the sum of the variance of the sum is the sum of the variances. But in this case, I don't think they're independent. Actually, maybe they are independent, and that would be really good. Actually, maybe they are independent in this case. That would be pretty cool. So you can try that calculation. Actually, I kind of have a feeling they are. No, they're probably not independent, but it might work out anyway that the variance of the sum is the sum of the variances. But anyway, yeah. So if A and B are independent, then we do have the variance of the sum equals the sum of the variances. But in general, like what if A and B are negatively correlated? Then the variance of this is going to be lower. Oh, and I also made a claim that some people were squinting at, which is that the expectation of these two things is going to be the same if you have the correct state value function. So my claim here, well, that's actually a pretty imprecise statement. So the more precise version of this statement is, what if we take expectation of delta t given state t and action t? I'm claiming that this equals expectation of, well, I'm claiming that this equals the advantage function if our shaping potential v equals v pi. That's claim number 1. And claim number 2 is that expectation of delta t plus 1 given state t and action t equals 0. Also, if this is satisfied. And the reason for this is, well, for the first statement, this is kind of what we already showed. This is just saying that the expectation of this term with respect to s sub t plus 1 is the advantage function. That just follows from the fact that this gives you the expectation of this thing is the q function, and we're taking q function minus value function. Now the other claim is that this expectation equals 0, and that's because the expectation of that's because in general expectation. I'm probably writing too low. Let me move up a little bit. So expectation of action sampled from pi of the advantage function equals 0. And this is conditioned on s. So if we just sample the actions and we condition on s, this is always 0. It follows that this thing is going to be 0 because you're conditioning on the previous state and the previous action. So we're taking the expectation over a sub t plus 1 here. and as well as the state. We're taking also the expectation over like state s sub t plus 1, state t plus 1, and so on. But we have an expectation over a t plus 1, and so this is going to come out to 0. Does this make sense? Yes.
So when you say the value function is the state value function, you mean that equality, right?
Yeah, I mean this. Yeah. Okay. So just as an application of these finite horizon estimators, this is something I showed it on a previous in a previous class also. So this is the A2C / A3C algorithm. And what it does is it does a finite set of time steps. Agent acts for t time steps, for example, for 20. And then at each of these time steps, you compute the discounted sum of rewards over that interval, like till the end of the interval you just collected. And you compute the advantage estimator here. And you also compute, so you have an estimator of the advantage and an estimator of the returns. And you can use this advantage estimator to do your policy gradient. And you can use the returns estimator to update your value function. So what you do is you compute the gradient of the whole loss by just adding these together and taking the gradient. And actually, the demo code in your homework is not that much different from, well, actually it is kind of different from this because you do the whole, you collect the whole episode, you don't just collect t time steps. I was actually thinking about implementing it like this, but it's a little more confusing to look at the code. So I figured I would give you the simpler version where you collect the whole episode, one episode at a time. Actually, the last question on your homework, which is the bonus question, is just I don't know, implement something, some other extension of the vanilla policy gradient method that we described in class. So one thing you could do is modify it so that it does this kind of thing where instead of collecting the whole episode, it collects t time steps, and it caps off all the returns with a value function estimator. So that shouldn't be too hard to implement, and you can see if that makes the performance better. One nice thing about doing it that way is it's actually much more suitable for writing really efficient parallel implementations because now your computation is in chunks that all take the same amount of time. So in the version that you have in the homework, it collects a bunch of paths, and each of these paths is variable length. So first of all, that's not so good if like one problem has episodes of length 10 and the other has episodes of length 10,000. Then you might have to tweak some parameters to make it work in both cases. But the other thing is that it's not so good for parallel implementations because then you have like if you try to parallelize this data collection, then you have chunks of work that are like variable length, and you're going to end up having like one worker wait for the other workers. Whereas if you do it this way, then each worker has to do exactly t time steps, so you can more easily like divide up the work and make sure everyone's synchronized in time. So this is how you make really good parallel implementations, whether they're asynchronous, like in this paper, the A3C paper, or you can do synchronous methods that are equally efficient using this kind of procedure. So yeah, just to relate it to this, we're using the advantage functions estimator we talked about here. Oh, and I'll show you some cool videos. So let's see. Where was it? Okay, where is the videos? So this was, so the night, I mean, people had known about these policy gradient methods for a long time, and this paper the method they introduced wasn't like that different from what people had been doing before, except it was using newer architectures like LSTMs and ConvNets that people hadn't been using like 25 years ago when this stuff was first proposed. But yeah, it wasn't that different of an algorithm, but it was pretty surprising to a lot of people that you can solve tasks like this task in a 3D maze where you have to like learn how to do the end-to-end mapping from pixels to actions. So here it's like they're running around and they're trying to collect these green apples. And it's running around a 3D maze. So I don't know, it's a pretty high dimensional input and a complicated function you're trying to learn. It's not super complicated because it's just like a green blob that you're looking for, but it's still pretty impressive and surprising to a lot of people when it came out that you can do this kind of stuff with fairly traditional policy gradient methods. Let's see, what did they also, was that? Okay, that's all I was going to show for A3C demos. And they also applied this to the Atari domain, which we talked about a few classes ago with the Q-learning results. These results are a little bit misleading when you're comparing it to Q-learning because it's looking at training time, but then that depends on exactly how you implement it. So I'd say it's more meaningful usually to look at, well, I don't know, it's interesting. It's just not, it has some caveats. But anyway, they show that you're getting much better training time with these policy gradient methods, with this A3C method than they were getting with the deep Q learning. It ends up in practice that it's less sample efficient by a factor, I don't know, some constant factor like 5 or so. It takes more samples, but it ends up being much computationally cheaper than Q learning. So you get much faster learning times. So actually, your homework assignment, you implemented DQN, and that took like, how long did it take to start seeing signs of life on Pong? I don't remember. What was that? Oh, someone? A million time steps or iterations? So hours or, yeah. Okay, yeah, so it's something like hours before you start seeing learning. And then it takes like several hours before it's learned on a pretty, before it solved the task. So with policy gradient methods, you can see signs of life much faster. Something like, let's see, I think it ends up being like something like 10 minutes. You're seeing the score go up like from -21 to like 19 or so, and then you can have it all solved in like 45 minutes or so if you have a good implementation. That's just running on a single machine with like 8 CPUs or 16 CPUs.
Is there any way to capture explicit learning, like if you're stumbling through this random walkish kind of process, and at some point you just learn something? Is there any way to capture that in the model so you don't have to push that through a million learning steps and you can just incorporate it?
So the question is there any way to capture some kind of explicit learning more explicitly, like
you're stumbling through that maze trying to capture the little bubbles,
yeah,
or whatever you're doing, and then at some point, let's say that you stumble, just to use a real world example, you
yeah,
stumble upon the magic map that tells you exactly where the thing is.
Mm-hmm.
How do you incorporate that knowledge directly, or look back over your last 100 actions and somebody said that is the one that caused you to get this reward?
Uh-huh.
How do you incorporate that sort of learning?
Okay, so just to repeat it for the video for the folks at home. So it seems like the question is, it seems like you should be able to more figure out like which are the good actions, or someone might tell you which are the good actions, and how can you incorporate that that information into learning. So the ideas we just described on shaping the reward function do that to some extent. So if you know the state value function exactly, then you know what the good action was. Then you can actually assign credit to different actions along your trajectory. So let's say you're trying to collect these green apples in the maze. There's a certain point in time when you first see the apple. And then if you were looking at the state value function, you would see it go up a little bit because now your network knows that there's a small number of time steps until you get it, assuming you hone right in on it. So instead of having to wait for the reward, you'll see it immediately because you'll know that something good happened once you saw it. And then your value function will also tell you when you're going in the right direction to move closer to it. So I think you actually do get at that when you do the reward shaping. the problem is actually you don't exactly do the right thing when you do reward shaping, because when you do, as I showed earlier, when you do reward shaping, all it does is it gives you a baseline. So it doesn't actually, assuming you have the perfect baseline, then reward shaping doesn't actually help you at all to estimate, it doesn't change your policy gradient at all. Like, if you have a perfect baseline, then shaping the reward doesn't do anything. Because of the telescoping sum. So the reason for that is when you do the reward shaping, yeah, it does the better credit assignment where your actions, it gives you, there's a lower delay between your action and the reward, and like shorter feedback or faster feedback. But you're still adding together you're still adding in all these future actions which are not dependent on the action you just took. So when you do the perfect reward shaping with vpi, now the consequence of action t happens immediately. It happens in the first reward, but you're still adding in all these other future rewards which depend on your other actions. So you're actually messing up your estimator by adding in future rewards. So what you really want to do is take your next action and then take your first reward and then ignore all the future ones. And that's kind of like what that's what these finite horizon methods are doing. But they unavoidably introduce some bias if your value function is wrong. So hopefully that gave some, helped a little bit. So anyway, so this is like what we've been talking about is these finite horizon estimators. Now we're going to go back and justify this idea that we briefly proposed earlier, which is that you use a more aggressive discount instead of doing like a discount of 0. So we have these finite horizon estimators that look like a sum of rewards that's capped off by the value function. And we're going to define the TD error like we just did over here. Okay, as we just showed, you have this telescoping sum, which lets you write the advantage estimator using a finite sum of these TD errors. And so what we can do is, okay, each of these advantage estimators is reasonable. It's a reasonable estimate of the advantage function, which gives you, which is unbiased when you have the correct state value function. So when v is actually the state value function, then each of these is unbiased. So that means they're all kind of reasonable to use. Unfortunately, when you have the wrong state value function, which is the case in practice, the ones with small k have high bias, and the ones with large k have low bias. So so what you can do is just take an exponentially weighted average of all of these. Oops, this should say times 1 minus lambda, so that it's actually an average. Let me write this properly. So we can define a superscript lambda sub t to be 1 minus lambda times a superscript 1 t plus lambda times a 2t plus lambda squared times a 3t plus, and so on. So we're taking the exponentially weighted average. And then you can do a little bit of, you can just kind of write out this sum and move some symbols around, do some bookkeeping on all your terms in the sum. And I encourage you to do that calculation if you're curious. And then you get this very nice looking expression, which says that you have a discounted sum of your Bellman error terms, or your TD errors, but it's with a more aggressive discount, gamma lambda instead of gamma. So it's like what we did is we shaped the reward function using value function v, or as our shaping potential, and then we pretended the discount was lower, or we had a discount of gamma lambda, so a more aggressive discount. And that's based on the intuition I was just explaining before, that we want to ignore the rewards that are more in the future if our value function was good. And so this method, when you put it all together, is called generalized advantage estimation because, why do I have the wrong formula in all these places? So this should say 1 minus lambda again. So this is just what we did on the previous slide. We have the telescopic sum. We take the exponentially weighted average. We have this lambda estimator. This scheme is called generalized advantage estimation. It's appeared a bunch of places, but not exactly in the same form. It's related to TD lambda, which is a way of doing value function estimation. So people have been talking about TD lambda for a while, where you do a backup on the value function that involves this exponentially weighted sum. But people hadn't really used it so much in policy gradients. I'll show you a cool video. Let's see. So this was from some of my colleagues and I. So what we were trying to do is learn how to do locomotion with a we have a 3D humanoid robot, and the observations are joint angles and joint velocities and Cartesian positions of everything, but still pretty low level. And the actions are just joint torques updated at 100 hertz. So it's a pretty low level representation of the input and the output. And then we applied this generalized advantage estimation method along with trust region policy optimization. And so we start off with a random policy, which is actually this is so we have this is a stochastic policy that's predicting a Gaussian distribution and then sampling from that Gaussian distribution. So that's exactly what you're implementing on the homework for the pendulum problem. You're going to just take a network that outputs the mean of a Gaussian distribution. You're going to implement the same kind of network we used here. So once your network works, I think you could actually get it to work on really hard problems if you just like scale it up, like collect more samples and tune the parameters right. Yeah, so anyway, even with the single core implementation actually. So I think if you just take your homework implementation and you tune all the parameters right, I think it can solve this 3D humanoid problem in like, I don't know, like a day or so. So anyway, you start off with a policy that kind of falls over, but then it starts falling over more and more slowly. And then eventually it figures out how to walk. And eventually it figures out how to run pretty nicely. And it's really stable at the end, so it'll just run indefinitely for like hours. And the same algorithm we applied to this a different kind of robot without making any changes to the algorithm or the parameters. So the nice thing is previously people have been able to do simulated 3D humanoid locomotion for a while, but all the methods that people use are very like domain specific. So they'll be based on deciding where to plant the foot, and they'll be based on some intuitions about how to do footstep placement. But here we apply the same algorithm to some totally different looking robot. And we could also apply it to figuring out how to get up off the ground. So here we just define a different reward function, which is what's the height of your head, or what's the difference between your height and some target height squared. And then it just figures out how to like swing its body in order to get up off the ground. Let's see. You can actually try both of these things. So both of them are in gym. So one of them is called humanoid V1 and the other is called like humanoid stand-up. Yeah, so let's see. Oh, that's okay. Back to my slides. Oh, I closed Keynote or it crashed? Oh, I had skim. That's where I was. Okay, so I think that's all for today. Okay, I had some other policy gradient material, but I'll save it for next class. All right, thanks for your attention. Yep, and it'll be in the Newton room.